Hello, everyone. And I want to talk about the equivalence principle today and what the implications are and how it relates to certain things in general relativity, such as the compatibility condition for the metric. And but let's start off with some special relativity real quick. So in special relativity, we have the Minkowski line element given by our standard here. So, and for now, I'm gonna keep track of my factors of speeds of light, and I'm just gonna call this dx squared, where dx in my notation is just some vector here, dx vector squared. And I also want to introduce an affine parameter, which in special relativity and most of the time in general relativity, we just use proper time. So tau is going to be my proper time. And then the reparameterization for my line element will look like this. And I'm going to use the convention where I have minus c squared d tau, just because I'm using general relativistic convention, and I'm keeping track of my minus sign on the temporal part of the line element. Now, so when I do this, I have c squared here, dt squared, and this will give us a relationship minus between the usual time dilation relationship between proper and improper time. If I rearrange this equation a bit, so on the right side, I can factor out a minus c squared dt squared here, which would give me 1 minus, and then I'll have 1 over c squared dx squared dt squared. And so we see that as our beta squared factor, where keep in mind we're always keeping track of ratios of velocity versus c in terms of beta. So here I have a minus c squared dt squared, and then I have 1 minus beta squared. Yeah. And so comparing this to what we have over here, we get our final relationship. We get minus c squared d tau squared equals minus c squared dt squared, 1 minus beta squared here. And then we can cancel out these factors, and let's write this as dt over d tau, which then becomes 1 over 1 minus beta squared square rooted. Right? And that's what you call gamma. Right? So neat little result from the Minkowski line element. Let's look at let's start looking at our space-time coordinates real quick, and we'll come back and use. So we'll be making use of this here in a second. And remember, we're still trying to get to the equivalence principle. And so let me start off by writing out my space-time coordinate. That's going to be c, t, and then my x here. And what I want to do is look at what's called the four velocity, capital U, and we'll give it some index mu, which is in general defined as the proper time derivative of my coordinates, which if I look at my coordinates, I'm going to have, that'll be c d t d tau, comma. And what I'm going to do, I'm going to do some chain ruling here. I'm going to do dx dt dt d tau. And so we can recognize this as, well, what I'm going to do, I'm going to factor out a c here, and the dt d tau, which remember is just our gamma factor. So I'm going to factor that out as gamma, and so I'll have 1 here. And then if I factor out a c here, I have to factor out a c over here, so I have the velocity over c, so that'll be beta. But it's my 3 velocity, so I'll give this beta a little vector sign to tell you it's the ratio of each component's velocity over, or the component of the 3 velocity over c. So that's nice. That's our 4 velocity. And the next thing I want to do is look at what happens to the square of the 4 velocity. So I'm going to take u squared, which we may write as u dot u, or if we actually want to calculate it, we'll introduce our Minkowski metric here, and our 4 velocities here, where keep in mind eta mu nu is just the Minkowski, so it's minus 1, 1, 1, 1, 0, 0 here. And so if I look at this quantity and I look at this quantity, I can see well, I'm just going to have a minus this term squared plus this term squared all times this term squared, right? So my 4 velocity looks something like c squared gamma squared minus 1 plus beta squared. And I can drop the vector over the beta now. So what do we have? Well, remember that gamma is 1 over the square root of 1 minus beta squared. So squaring that just squares this, but then I have this on the top. So I should just be left with the minus c squared here. So u squared equals minus c squared. And keep in mind that the reason I kept my factors of c is because it doesn't matter who's observing or who's in what gravitational field or not. You know, if it's a flat gravitational field like the Minkowski metric, or general gravitational field that you get from solving the Einstein field equation, everybody measures the same value for c, right? So this is an invariant. And that's what Einstein, that's one of Einstein's first postulates, right? So this is an invariant quantity. So what does the principle of equivalence say? Well, Einstein had this famous thought experiment that if I took a person on Earth and encased them in a closed box or container or something, so I have a person in here, and then you draw the free body diagram for this person, right? They would be experiencing mg, the force downward, right? And then of course there's a normal force. But now you could remove this would be the Earth, right? And let's say now we remove the Earth, and let's just have the box here. And there's no windows in the box. That way the observer, the person inside, doesn't know whether or not they're standing on the Earth or not. So, which is the key. Yeah. And now instead of being on the Earth, we're just going to accelerate the box at the same value of the gravitational constant g in free space, right? So this is so here you're on Earth, and here you're in free space, and the free body diagram should look the same, right? So for this person, there's again going to be a normal force due to the box, and then a force of m times a, which is mg this time, because it's the same value, right? So a person in a closed container can't tell a difference between being accelerated in free space at the same value as g, or being stationary on the surface of the Earth and being pulled down by gravity with the value of g on the Earth's surface. So that was Einstein's famous thought experiment, and that's how he coined the equivalence principle. Okay, so I'll just call this equivalence principle. I'll just use a shorthand. EP, let's call it EP. So that's our equivalence principle. But what's a good way to write this down in terms of our mathematical formulations of special and general relativity? And that's where we come back to this. Okay, so since this is an invariant quantity, what does that mean? It means that locally, every gravitational field should be able to be described as a flat gravitational field, replacing a gravitational geometric effect with an acceleration. That's what the mathematical way of describing the equivalence principle is. So that means that the equivalence principle implies that c squared minus c squared equals u squared is true for any gravitational field. Okay, where g mu nu comes from solving the Einstein field equations, right? R mu nu minus 1/2 g mu nu r equals 8 pi g t mu nu. So that should be true. So this statement is true for any g. That's the equivalence principle. That's what the equivalence principle. That's a way of of saying it in a rigorous differential geometric or Riemannian geometric equation or way, saying that g mu nu u mu u nu equals minus c squared. In most books, you'll see this equation written down where they've set the value of c to 1. We can do that, but it's really not we're not inconveniencing ourselves too much by keeping track of it. And I like to show it for pedagogical reasons because it shows that this is an invariant here. So now I want to talk about, so now we've established what the equivalence principle means general relativistically with the rigorous mathematical equation. So I'll keep that there. Now I want to talk about how does this relate to, how does the equivalence principle relate to metric compatibility. So metric compatibility is the fact that the covariant derivative of my metric is set to 0. It's a gauge choice. Most people call it a gauge choice, but it's a choice that you can make in order to fix your connection in the covariant derivative, right? So normally the covariant derivative, if I think about the covariant derivative acting on a vector, right, that's going to tell me how the vector components change when you parallel transport it across a curved surface, right? So you have to compute the regular derivative, and then you have to add the effects of curvature to it here in a certain way. However, due to the differentiable structure of any curved surface, I can pretty much define an infinite number of differentiable structures, so I have an infinite choice of connections to make. So one choice to fix that is to introduce this, right? Metric compatibility. And what happens when I introduce metric compatibility, let me write this out. So when I introduce metric compatibility here, I have g mu, and so that'll be the regular derivative minus, since it's covariant gamma, and then I have let me introduce little gamma here, alpha mu g gamma nu minus gamma alpha mu g mu gamma. And keeping in mind this equals 0. Okay. And this equation, like I said, fixes capital gamma, my connection. Why does it fix that? Because I can permute this equation in the three indices, and then I'll have three equations and one gamma to solve for. But you'll see that let's just do it real quick. It's not that hard to do. So here I'm going to permute my indices here. And when I permute my indices here, so I get this. Oh, and I forgot my g mu nu here. Apologies. Okay. And I'll use that same dummy index here, but now here I'm going to have mu g gamma alpha minus gamma, and then I'll have mu alpha g mu gamma, and that still equals 0. So I haven't changed the equation except permuted my index structure. And let's do the last permutation. So that'll be mu g alpha mu and then repeating the same thing here. And this too still equals 0. And what am I going to do now is, since they're all equal to 0, I'm going to add and subtract all to the top equation. Okay. The other thing we assume is we got to assume a symmetric connection, meaning that there's no torsion. So any alpha mu is going to equal alpha mu. And we already know the metric is always symmetric for Riemannian manifolds, which is the natural language for general relativity. And so with these assumptions, right, what happens next here? Let's take a look. So I'm going to have this term plus this term minus this term. Okay, let's go ahead and write that down. So I'll start writing down my equation. So I have 0 equals and then plus d mu g, and let's see, mu alpha minus. Okay, so I have this term. Now, if I look at this Christoffel symbol and this one, there are, all the indices are the same, right? The metric is symmetric, and we already assumed that the connection is symmetric. So I get a -2 of this. I get minus 2. Let me highlight. So I'm looking at this term and this term here, and I get -2 little gamma, and I'll just pick alpha mu g gamma nu. Now this term here is right here, but since I'm subtracting this term, that means these terms will cancel, right? So I have almost the same index structure here. All right, so that one cancels. And the last one here, again, this one, and that index structure, and it's opposite, we're gonna have opposite signs. So these two cancel. And so So this is my only equation left here. And now, like I said, this allowed us to single out one single gamma. And so now we can solve for this one gamma by bringing it to the other side. I'll keep the metric on it for now to avoid confusion. So I have 1/2 times this, and I'll have alpha g, and I'm going to write mu here and mu here because metric is symmetric. And then, but you'll see why I wrote that, and because it doesn't change for this one either. And you can see I'm just flipping the alpha and then mu here for the first two terms, and then minus nu, and then this is already g alpha mu, right? Okay. The last thing I want to do is get rid of this metric, which we can do using the inverse metric. And so using the inverse metric, I then have gamma alpha mu equals 1/2, and then it'll be the inverse of that. So I have gamma nu here. Okay. And so this is the famous Christoffel connection. Some books will call it the Levi-Civita connection, which the Christoffel symbol belongs to the class. All Christoffel symbols are Levi-Civita connected. Okay, so like I said, this is our standard result for general relativity. But let's look at how does this relate to the equivalence principle, because I've already said up here that the metric compatibility condition is the same as our equivalence principle, or it's another way of mathematically saying the formulating the equivalence principle. So I'm going to go back to the line element and look at, but this time we're looking at a general line element. And what I want to do is just rewrite this in terms of a fine parameter again. So I'm going to say my coordinates x mu are functions now of an affine parameter. And so I can write this as g mu dx d tau dx nu d tau squared. And what we want to now do, but I know I know this here is an invariant, right? That's what we have up here. Okay, so I know it's minus c squared. But before I imply that, I want to be able to calculate the trajectory of a point particle within this gravitational field, right? That's what we call that would yield geodesics, right? If so I know it's negative. So one thing we're going to do is when we take the square root, we're going to add in the negative sign by hand and define what's called the action for the point particle. So now I have the point particle action, which is just the square root of this, and then integrating out. So I'll call this S, since we call this ds. And then I'm integrating over d tau now, and then I have minus g mu nu dx mu d tau dx nu d tau, and then we're square rooting this. And like I said, we just want to have a positive factor inside the square root. And that's just from our general relativistic convention. And what do we do now is we apply Hamilton's principle. And for stationary actions. Okay, so we're going to vary S and set it to 0, keeping in mind that we have the endpoints fixed. So whatever our, so if I have a starting point here and a starting point here, and I'm looking at my path between the two, x mu, I'm going to say that at the boundary here, x is fixed. That means that the variation of x here, and then we could call this A and B here. So the variation of x at A is 0, and the variation of x mu at B is also 0. So we have stationary points, and we're looking at extremizing the action in between those 2 points, right? That's your standard Lagrangian mechanics, right? And in this case, it's more of a Lagrangian field theory because we have fields involved, and we're varying with respect to, you could call x mu a field, and even though it's a coordinate, but the principles here are going to be the same. So what does that imply? That just implies that there's no boundary contribution, no total derivative is going to change the physics of this action here. So let's perform this variation. So now I have, and we're varying with respect to x, the coordinate here. And so when I take a variation of this term, I'm going to have to do some chain ruling here. So I'm going to get I'm going to write this as, actually, let me write it off front. There'll be a -1/2 factor here. There'll be a minus g mu nu, and I'm just going to write this as u, just save some time. So the -1/2, and then your chain rule. So I have the variation of, and I took that minus sign to the front. So I just have g mu nu dx mu, and I'll write this out here because we're actually going to work with this term. And now we invoke the equivalence principle. And the reason why is that there's too much going on here that I don't want to deal with this anymore. I want to invoke my equivalence principle here and say, I know that this is going to be minus c squared modulo this, this minus sign. So this term should only be c squared here to the -1/2. So that means my total action is now going to be -1/2c times the variation of g mu nu dx mu d tau dx mu d tau. So again, so going from here to this step, we invoke the equivalence principle. So let's see what invoking the equivalence principle does for us and calculating this variation. So let's go through. My iPad's not cooperating. So here I'm going to have 3 terms. I'm going to have the variation of g mu nu, okay, and then I'm going to have dx mu d tau, dx mu d tau, and then I'm going to have plus 2 times g mu nu, and then I'll just use the first one. And that won't be. It'll just be dx mu. Since the metric is symmetric, we can just write this like that. Okay. Now we'll do two things. We'll do a chain rule, and then we'll do an integration by parts here to isolate the terms we need or want. So here I'll have alpha g mu nu, and then I'll have the variation of x alpha here times my dx mu d tau dx mu d tau. Here I'm going to have a minus 2 times the total, or the, not the total, but the derivative of g mu nu dx mu d tau, and then variation of x mu out front here. So that's just moving this derivative here. And again, since we're using Hamilton's principle, I don't have to worry about the total derivative term, because that would be a boundary term. So we'll just ignore that. But anybody's free to work out those details. And you'll see. Now I'm going to take out a dx alpha. So I'll change this mu and this mu to alpha. And I can see what I'm left with then. Okay, so here I have partial alpha mu dx mu d tau dx mu d tau, and then I have a minus. Let me go ahead and work this out. I have a minus 2, and then what I'm going to do for the metric term is do another chain rule. So I'm going to have d alpha here, g mu nu, and then I'll have a dx alpha d tau here, dx mu d tau. Oh, I probably shouldn't have done it like that. It might be too many steps right now. Let's just let's factor out first the variation term. So I'll just leave this as 2 d tau, because I'll end up changing too many indices at once. Now I might even get confused, but I know this will probably be easier to follow for the audience. And like I said up here, what I wanted to do was change this to alpha. So I'm going to change this to an alpha, and then have the total variation of x alpha outside. So, okay, now the next step, let's expand this derivative term using your Leibniz product rule, and then also using some chain rules. Okay, so I'll have a minus 2, and then the first one, like I said, I'm gonna I'll just reuse my index mu since it's not being used here. I'm gonna have alpha mu and then dx mu d tau. So that's just chain rolling this derivative acting on the metric, and then plus g alpha nu, and that'll just be a second derivative now on that. And it looks like I've dropped this term here. Let me put that back in. I'll just write it more compressed. And so the way I planned it was convenient, because now I have a mu. So what I want to do is factor out this term from this and then from this. However, keep in mind this is symmetric. So I can interchange these guys. But this is not necessarily symmetric here. So what I need to do when I factor out this term is symmetrize over these two and divide by a half, which will cancel out that -2 for us. So what I'm saying, this is going to look like here. I'm going to have alpha g mu nu, and then I'll have minus d mu g alpha mu minus d mu g alpha mu. And there would be a 1/2, but there's already a factor of 2 there. So I don't need to worry about that. And then I have dx mu, d tau, dx mu, d tau, plus the last term, g alpha mu, d squared x mu, d tau squared, all times dx alpha. Very good. You might already starting to recognize something here, but let's just keep going. At this point, what I want to do, let's oh, did I drop my C? Yeah. I'm so used to seeking one. It's I'm just going to run this -1/2 through the equation. And so that'll give me a factor of 1/2 here on this term. And I'll write the first one. I'll write it like this. The minus signs become positive signs. So I'm going to write them first. And then this first term now is negative times this term minus and oh, it looks like that. It should be plus, right? Because I lost my that minus sign. Should have made that minus there. So I had a small mistake here. So that'll be plus g alpha mu okay. And now the last thing I want to do, and this is really just for convenience, is I want to lower this alpha, which means we have to raise this alpha and add an inverse metric here to raise it. Raising this one just turns it into Kronecker delta, which makes that alpha. And then here we'll have an inverse metric. So last thing I'll do now is 1 over c d tau, and I'll have 1 over 2. And then I'll have a g, and then there'll be alpha, and then I'll need a nu, right? And then I'll write this, no, that's not right. Yeah, I don't want to use nu because I already had nu being summed over here. So basically what we're going to do is just replace alpha with some summed over index. So I can use little gamma again. And then that raises that alpha now. Oops. And then here I'm just going to be left with, like I already said, dx alpha d tau squared. And now here I'm going to write my alpha on the bottom. And I know this is not canonical. It kind of might disturb someone, but it allows us to pick off the uh, the canonical form of our geodesic equation. So remember, all of this still equals 0, so we get our field equation as d squared x alpha d tau squared plus. And what do we have here? We have 1/2 g alpha gamma d mu g gamma nu plus d mu g gamma mu minus mu on this equals 0. But if you remember, this was also a result up here from the metric compatibility, from setting the covariant derivative to 0, right? Gave us this form for the connection, for our connection. And you see it's the same. We have nu, we have a gamma here. And instead of mu, I have that. The index structure is a little different, but I shouldn't say it's different. My indexing is different. The index structure is the same. Okay, so what happened? First of all, coming down here, what I can say is that, see, I'm summing over gamma here, mu nu on the bottom, mu nu, and then alpha on the top. So this has become, I can write this as, and then a big gamma alpha mu nu. And most of you probably have already seen this. This is just a standard geodesic equation. So it's a geodesic equation, which we arrived at this geodesic equation in terms of the Christoffel connection because we invoked the equivalence principle here. That's why, so invoking the equivalence principle reproduced metric compatibility. So that's why the covariant derivative of a metric equals 0 is equivalent to the equivalence principle. Yeah, so we'll end here.